All right, so we will continue with the topics from last time. Before I go into repeated trials, let me just one more time talk about independence. So remember, if you have events A and B are said to be independent, if this is true, probability of their intersection is the product of their probabilities. And if you have three events, so maybe this is something we didn't discuss last time. Anybody, when do you say, using this logic, when do you say A, B, C are independent? Anyone? What would be the conditions? You have three events. Yes? So if A, B, C are independent, so you take two at a time. They are independent if this is true. So you get this is equal to PA multiplied by PB. Then what? What else must be true? Anyone?
All the pairwise.
Yeah, you need all pairwise. So BC would be PB multiplied by PC. And the third one is PAC is PA multiplied by PC. Anything else?
Combined probability of that.
What is that?
Everything should also be separate.
You have to talk about, I didn't hear you.
So probability of ABC should also be probability
All
of
right,
A.
so right, that's a good point, because then you also have three of them. So you could also say that the intersection of ABC must be the product of PA multiplied by PB multiplied PC. So this is the additional condition. So you can see that there will be more and more conditions if you have four sets, etc. So let me give you an interesting problem. So this I wanted to talk last week, I forgot. So let's say we have a set of events A1, A2, etc., AN that are independent. And I'm going to define A to be A1 union, A2 union, etc., AN. Remember the definition of independence, it is not for union, it's for intersection. Whereas here I have asking, so the question is how do you find this? So in fact, let me ask you this, if A and B are independent, how do you find A1 union A2? Anyone? What is the probability of A1 union A2? Anyone? Independent or not, how do you write the probability of A1 union A2? PA1?
PA1 plus PA2 minus PA1 A2.
All right, so if A1 and A2 are independent, what happens to the last term?
We don't need the last term.
You need the last term, but it becomes the product of PA1 multiplied.
Yeah.
Okay. So question is, how do you do this here? Here, you problem is there are too many sets. So the easiest thing is to use the complement. So anyone remembers what is the complement of a union? Anyone?
All of them, like A1 bar, intersection A2 bar.
Intersection, not union. Intersection. So this is what interesting. Here, remember, here it is union, here it is intersection. But if A1 and AN are independent, remember you are supposed to show that their complements are also independent, right? Yes? No? Remember,
Yes.
I gave it to you as a homework. If A and B are independent, show that A bar and B bar are independent, right?
Yeah.
So then all these are independent. So that way we get the product of probability of A bar is the product of the probabilities, I equal to 1 through n, probability of AI bar. But that's the same as 1 minus PA. And so we get probability of A is 1 minus PA bar, which is, so this is a very useful formula. Okay, so if A is A1 union A2, etc., so I'm going to give you an example. So let's say DI stands for the event that this is some number I causes a death to a person. And D is so remember, what is the anybody? What is the relation between? Let's say there are n diseases, D1, D2, etc., Dn, and D stands for death to any person. So what is the relation between DIs and D? Anybody? DI is death due to any one cause, any one disease. D
The union.
Union of all these.
all right, very good. So D can cause, death can cause because of D1 or D2 or D3, etc., Dn. Let's say the probability of the death is very small. I'm going to call it P. It's very small. Let's say 10 raised to minus 5 something. Okay. So the question is what we want to find. If the so what are we saying? The death can happen due to a large. Let's say there are a million of them, very large number. So I'm going to call. So let's say I'm going to call this small p. So anybody, what is the probability of D from what we said? And it is reasonable to assume that these causes are independent. So this is a judgment call. Okay, we are saying disease 1 has nothing to do with the disease 2, etc. You can, whatever is the cause, automobile accident or cancer or whatever. It doesn't have to be disease, call it cause. Okay, but everything is extremely rare. So according to this formula, look at here. Probability of death is 1 minus, I'm going to apply this formula, 1 minus p to the power n, because all the diseases I'm going to assume have, or you can write it pi here, but I made it all equal. Now just to show you something, let me say p is very small, p goes to 0. So I'm going to assume that p goes roughly as 1 over n. I hope you are following me what I am trying to say. P is the probability of death due to any particular disease, any particular cause. So this becomes 1 minus 1 over n to the power n. Anybody has any idea what is the value of this number as n becomes larger and larger? 1 minus 1 over n to the power n?
1.
What?
1
1 is wrong.
guess it's 1 by E.
There's 1 by E. You see the difference? So that's 1 by E. Why 1 by E? You better check your math. Look at the definition for E. In other words, I'll write it here. E raised to minus x is limit n tending to infinity. Try to derive this formula. So put x equal to 1, you'll get what I said. And how much is 1 over E? What is the value of E? Anybody? E is how much?
2.3, I guess.
All right, so 2.7. So 1 over E is approximately how much?
0.25.
0 point? Let's say 1/3. Is that good? Take it as 1/3.
Okay.
I'm saying E is close to 3, right? 2.7 something, right?
Yeah.
Yeah, so let's say 1 over E is 1/3. So what is 1 minus 1/3?
It is 2/3.
Yeah, about 65%. So what the moral of the story is, because of the large number of causes, the probability of death is likely. It is more than 0.5. Of course, everyone will die at some point. Right?
Professor.
So this is about 65%. Hold on, let me write it down. 0.67, roughly, approximately. Okay, what is the question?
Professor, can you send me as a host? Some students can't join in. I want to check what happened.
I keep writing admit all. I have to get rid of this. Okay.
Some students seems in waiting room and can join.
What did you say?
Some students seems in waiting room of they can't join in class.
All right, let me try to get them. No, only two people are waiting. I
Oh,
just.
can you set me as the host? I will check what happened.
Can you ask them whether they are in? Everybody is in?
Pardon?
I'm saying I admitted everybody. My God, this is. I need to change this sport. All right, so why don't you, to avoid the confusion, why don't you send a, I hope you understood what I said, which is to everyone, the quiz is going to be at 7 p.m. All right, so we are back to this problem. So the probability comes out to be roughly, if so, the moral of the story is if an event can cause due to a large number of events whose probabilities are extremely small, because of the large number, the fact that something will happen is likely. It is more than 0.5. It is 0.67 approximately. All right, so this is what I wanted to say. And again, those of you who missed it, try to see how this expansion comes. Easiest way is expand this as a binomial, so that will go 1 minus n choose 1 x, etc. So n choose 1 over n, etc. So you try to expand this in binomial, then you put the e raised to minus x expansion. And then you will see that this expansion goes to this. That's the way that you should try to prove it. So let me come to repeated trials. So far what we have studied is a set of all elementary outcomes, and then maybe the subsets here form A, and we figure how to associate probability. I'm going to write it as S1 and probability as P1. I'll tell you the reason why. So the probability, of course, satisfies three axioms. Probability of the whole set is 1. Probability of any event is non-negative. But most importantly, if two events are mutually exclusive here, probability of their union is the sum of the probabilities. Now suppose you have another sample space. I'm going to call it S2. And the elementary outcomes, I'm going to write it here by eta I, eta j. And the subsets here, I'm just going to denote it by B. Here the subsets are A's, here the subsets are B. So using this again, we can, all that I said about here is true about this experiment also. So remember, we have two experiments. Maybe it is the same experiment repeated, or it could be a different experiment. So this could be tossing a coin, and this could be tossing a dice. So the dice has got 6 faces. So here the outcomes will be F1, F2, F3, F4, F6. Here there are only 2 outcomes, head and tail. And we know the probabilities of the elementary outcome here is P and Q. Here it is if the dice is unbiased, it's going to be 1 over 6, etc. And again, probability of any event here again satisfies all the axioms of probability, etc. Now, what we want to do is how do you combine these experiments? In other words, if you look at the outcomes of a combined experiment, it could be we are repeating it, or as I said, we may be being simultaneously conducted, like tossing a coin and tossing a dice, or tossing a coin one after the other. In any case, at the end, we want to consider the combined experiment. So you can clearly see when I say combined experiment, what I would ask is, I want to have an outcome from here, and I want to have an outcome from here. This would be the, for in some notation, I'm going to use this Cartesian product to denote the combined experiment. So the notation wise, I'm going to write it like this. So so remember, if this is a bigger space and there will be some outcome, let's say alpha I, alpha j, etc. By alpha I mean, remember, it has got two components, one component from here and one component from here. So by alpha I, obviously I must be meaning some output from S1 and some output from S2. And this is just for two experiments. So if you are combining multiple experiments, this will be like a coordinate system, a Cartesian product, and any elementary outcome here will have n tuples here. So in general, this will be psi I1, psi I2, etc., psi IN. Each of these referring to one of these experiments. So the question is, if I have, so this is the combined experiment. Why I call it repeated is if the same experiment is being repeated, in other words, if you have a situation where all this, the same S is being repeated n times and creating a larger S, and then this is a repeated trial because whatever is the S1 is being repeated n times. So if I call an elementary outcome alpha here, and an elementary outcome here is psi I1, an elementary outcome here is psi I2, etc., then this would be, as I said, psi I1, psi I2, etc., psi IN. So this will be an n tuple. There are n entries, each entry corresponding to an ordered entry from the original experiments. So let me concentrate for now on two experiments, S1 and S2, with the outcomes. I'll denote it differently. Psi is and let's say eta is easier to understand. So an ordered pair from here will be one entry from here and one entry from here. In order not to create confusion, I changed all the, and if an entry here is alpha I or alpha ij, then this alpha is going to typically look like this. Again, the notion of independence is pretty clear here, right? So we say these experiments are independent if the product rule holds. So the question is, how do we define probabilities? We know how to define the probabilities for each of these experiments. So the probability of the combined event is going to obviously depend on the probabilities of this. Now I am going to give an additional condition that these experiments are done independently. What that means is here, the probability is going to be the product of the probabilities. So why I write P1 and P2 here is in order not to create the confusion, because we are dealing with S1. It has one way of assigning the probabilities. We have dealing with S2, it may have a different way of assigning the probabilities. Of course, the probability satisfies all the axioms. And if these experiments are performed independently, then what that means is the probability of a combined experiment is our combined outcome is the product of the respective outcomes from each group. So this is where the independence comes in. So if this is a coin, we know, of course, what we mean by independent trials. You toss the coin once, then you toss it again. So the idea is that you clearly can see there is no way the first toss could have influenced the second toss, unless during the first toss you toss it into oil or something, and then the coin becomes weighted and so on. So that's not, so none of that is happening. If none of that is true, then you can assume these experiments to be not influencing each other. And if these experiments are identical, then you don't need these suffixes 1 and 2, etc. So let me go to a general case where I have the big experiment is the product of the Cartesian product of the same experiment, let's say repeated n times, or n different experiments, either way. Then, as I said, if these elementary outcomes here I mark by psi I1, psi I2, psi j1, etc., psi ij, etc., this is the jth one according to our psi in, then the elementary outcome here, any psi I, will be an ordered pair of one entry from here, a second entry from here, etc., another entry from here, the last one. And the product of this psi I would be, if these experiments are independent, then this would be the product of the elementary probabilities of psi I1, probability of psi I2, etc., probability of psi. I don't have too many different symbols to write, otherwise you could use different symbols, but it should be clear from the indices also. So with that in mind, let me do a concrete example. And of course, maybe to do a little bit generalization. So again, once going back to S1 and S2, so if there is an event A here and event B here, probability of A is well defined here, probability of B is well defined here. And as I said, the Cartesian product of the two, we will denote it as A cross B, and the probability of A cross B would be, of course, here. What that means is A belongs to the first experiment and B belongs to the second experiment. So the probability of this event is going to be, if S1 and S2 are independent, it's going to be P1A multiplied by P2B. So that's the way we are going to compute. So for independent experiments, the probability of a general event A cross B is defined through P1 and P2. It is P1A multiplied by P2B if they are independent. If it is not independent, it gets to be more complicated. So as an example, this is a good example, we'll toss a coin n times. So we'll continue with this example for a while. So this is a repeated experiment. So the first toss, you will have head or tail. I'll write it like this. Second toss, you will have head or tail, etc. Ith toss also you have. It's the same coin, so I don't have to write H and T. Cross the last toss also. So the sample space for each one of them is head or tail. So I have S1 is head or tail, S2 is head or tail, SI is head or tail. So and S I'm going to write it as the Cartesian product of all this. So the Cartesian product simply means it's a fancy way of saying that I'm tossing a coin independently n times. And independence is a jump in faith, in the sense that we know how the experiment is being performed. We take a coin, you toss it, it falls down or you catch it in your hand. You haven't destroyed the coin, or you haven't heated it up. You haven't put it in paint. So it's exactly the same coin. So if you toss again, the first experiment has not influenced the second experiment. So we will say that they have nothing to do with each other. Remember, so you go to the conditional probability. Probability of A given B is PAB divided by PB. If B has nothing to do with A, that means A and B are independent, then PAB becomes PA multiplied by PB divided by PB. So conditional probability of A given B is the same as PA. So that's another way to look at independence. If two events are independent, then they are not influencing each other. The conditional probability of A given B is exactly the same as PA, which is the case here. So we can say all these experiments are independent. So the question is, what is a typical psi here? So remember, you can take any one of these combinations. So a typical psi would look like this. You could have a head here, then you could have a tail from the third one, tail, head, etc. A sequence like this. So this is a typical sequence. When you toss a coin n times, so I'm going to write I, because you have several sequences like this. Remember, there is a sample space here. Each entry will look like this here. Each entry here will look like only very simple, head or tail. Each entry here is head or tail. Whereas here, it's one entry from here, another entry from here, one entry from here, another entry from here, etc. So a typical sequence is going to look like this. So the question is, what is the probability of this typical sequence? So that's going to be from what we discussed earlier. Somewhere here, the probability is going to be the product of the probability. So this is going to be probability of head, the way I have written, another probability of head, probability of tail, etc. Probability of tail, probability of head. So let me, probability of head, I am going to call it P. Probability of head, I am going to call P. So this is PP. Tail, I am going to call Q. So Q is, of course, 1 minus P. So this is Q, and the last one is P, and this is Q. So, of course, how many P's are here? It depends on how many heads are here. So I'm going to start counting the heads. Look at here. I'm going to, this is one head, second head, third head. Keep heading. I'll get to some heads. I'm going to call it K heads. In which case, this will be P to the power K, and there will be N minus K tails. So this will be, so if you have K heads in N tosses, this is a specific sequence of K heads in N tosses. I hope you can read it. I'll read it to you what I just wrote there. What I wrote is K heads in N tosses in a specific sequence. Look at here. This is a specific sequence. It is true the total number of heads are here K, but I could flip these two. Still I'll get K heads in N tosses, but I'll get a different sequence. I could flip these two. I'll get these two I meant, or these two. I'll get a different sequence. So this is such a particular sequence with the K heads in N tosses. So let me rewrite what I wrote here. So if I take a sequence with I start counting this, I see that there are 1, 2, 3, etc. Totally N experiments. Look at here the way I wrote. N experiments, and I start counting the heads. These are the heads. 1, 2, 3, etc. K heads. So what you see here is a specific sequence of k heads in n tosses. And if the tosses are independent, what we have figured out is probability of the specific sequence is p to the power k, q to the power n minus k. Of course, k cannot be greater than n, so k is going to be a number between 0 and n, including both. When you toss a coin, you don't have to get any heads, or you can get all heads. Both are possible. But we notice that this is only one sequence, because I can flip any head and tail, I'll get a different sequence. So the question is, how many such sequences are there? Let me write them to be psi1, psi2, etc. psi n. I don't know how many are there. We will figure this out. But any one of them will look like this: h, h, t, etc. t. And in the next one, you can flip this. So, for example, this will be h, t, h, etc. h, and so on. So you can see by flipping the heads and tails, k heads, and you can create several sequences, all of which have the same probability. All of their probability, because they all have k heads in n tosses. And look at these sequences. When one of them happens, the other one is not going to happen. So they also have the property that psi a and psi j are mutually exclusive. These are mutually exclusive. When any one of the sequence happens, the other one is not going to happen. So remember, I told you last week, the whole goal of this course is to try to find the probabilities of complicated events from simpler events. So with this in mind, let me define an event. So we are interested in this following, suppose we are interested in this. K heads in n tosses. So you toss a coin n times. What we are interested is what is the probability of we are interested in this event. So k heads in n tosses. So let me, so of course this k could be anywhere from, k could be 0, 1, 2, 3, etc. n. So k is going to be an unknown which you cannot previously, which we will not know it unless the experiment is completed. This nature of this k. K is the number of heads. So you can see that beforehand, you cannot predict k. Another way of saying is that k is random. By random, you know exactly now. Once the coin is given, you have no idea unless you do the experiment how many heads will show up in n tosses. So it's a variable. K is a variable, and k is random. So I'm going to denote this k by this x, and I'm going to say this x is a random variable. X is actually representing this k. So x equal to k is an event. That means x is representing the random variable, which is the number of heads in n tosses. So that's a reasonable, so x is, I'll rewrite here, number of heads in n tosses. So if you, and it is pretty clear, x is random. Whatever is your notion of random, because x could be 0 or 1 or 2, etc. or n with the different probabilities. So if I make this notation x equal to k, it's very clear what we are asking. X is the number of heads in n tosses. So if I call this is an event, what we are asking is, define this event. What is the event is k heads in n tosses. So of course, what we are interested is we want the probability of this event. So you see where we have come. This is a complicated event. As I said, this is the whole point of this course, try to compute the probabilities of complicated events from simpler things. So keep in mind that if you go back a couple of slides, you can see that what we have is the probability of any specific sequence with k heads, we know the probability. But this is not x equal to k. This is just one sequence with the k heads. So if you take a typical sequence, psi I, this is a one sequence with the k heads. So we argued that these are independent trials. So we know that probability of psi I is, we also argued earlier, p to the power k, q to the power n minus k. The question is, how do you connect this with x? That's the question. Anybody? Let's say you looked at all the sites. We have psi 1, psi 2, etc., psi n. All these sequences have the property that they all have k heads. If you look here, there are k heads somewhere. All of them. Let's say there are such n sequences. Anybody, how do you relate this event A to these events? These are specific events with k heads. Here what we are asking is, what is the probability of getting k heads in n tosses? Anybody? How do you relate this complicated event A to these simpler events whose probabilities we know?
The union of all those events.
Alright, so that's the big step. What he said is correct. So let me write it what he said here. And they're all mutually exclusive, and the probability of any one of them is p to the power k, q to the power n minus k. So of course now we know that the probability of x equal to k is, so what will be the probability of x equal to k? Anybody? They're all mutually exclusive. Huh?
Summation.
Yeah, summation I equal to 1 through capital N, probability of psi I. But look at that, probability of psi I is here, and that doesn't depend on I. So this is going to be n multiplied by p to the power k, q to the power n minus k. Now the question is, what is n? So that's what we are going to do next. So that is easy, because let's take n chairs. That's a combinatorics problem, 1 to up to n chairs. And you have only two types of players, head or tail. And we have k heads and n minus k tail. So you know it goes this way. The first head can come and sit anywhere. So there are n possible, you understand what I'm trying to say. There are k heads here, and let's say there are n minus k tails. So let's take one of them. Many ways you can derive this. The first head can go, has n possibilities. And it will take one seat. Then the next head has n minus 1 possibilities. So the last head has got n minus k plus 1 possibilities. Then you will get, so many arrangements are possible. But among the heads, they are not distinguishable. They don't wear different shirts or something. So they are all indistinguishable. And remember, if they were distinguishable, there would be k factorial possibilities. So we divide by that. And that turns out to be the number of, so this is nothing, another way to look at it is this way. If there are, any one of them can go into the first one, and anyone from here can go into the first one, whoever goes first has n places to sit or select. That person selects one, then the next person has n minus 1, etc., all the way to 1. So that's n factorial. But among these people, the heads are indistinguishable, and the tails are also indistinguishable. So you divide their combinations by the possibilities they will generate, etc. But you can go from here. If you go this way, the numerator is n factorial divided by n minus k factorial. So one way or the other way, you get the number of such sequences that we can generate. So what are we generating? The number of, so the question here was how many such sequences can you, different sequences can you generate? So if I start counting this as 1, 2, 3, etc., capital N, we wanted to find out capital N. So capital N is given by this formula, N choose K, right? This is the way this is expressed. So all we have to do is substitute it here. So let me summarize here. Toss a coin N times. They're all they're tossed independently. X represents number of heads in N tosses. So remember, small n and capital N. So X is obviously a random variable because according to your notion, we cannot determine the value of X beforehand. So the X equal to K is an event. So the next question is, what is the probability of X equal to K? I just found it out. It's going to be N. N is N choose K, P to the power K, Q to the power N minus K. K could be 0, 1, 2, up to N. So this is N factorial, K factorial, N minus K factorial, P to the power K. Q is 1 minus P to the power N minus K, if you want to expand. So either one is fine. If you look at this, this is a binomial coefficient. So generally this is known as, this is called a binomial random variable. So the random variables have named because of some related properties. So I have sort of physically, I've introduced the notion of a random variable. Random variable is something we are interested in, but whose value cannot be predetermined prior to the experiment. All we can determine is look at its properties. We know what values it can take. In this case, it can take values 0, 1, 2, 3, etc. n. So we can compute the probability of that for each value of K, which is what we have done. Then why not plot it? So X equal to K means, once again, K heads in N tosses. When you put it that way, we don't really care about which sequence it is. All we care is what is the probability of getting K heads. It could be due to the first sequence, second sequence, third sequence, or the last sequence. So any one of them. So psi 1 or psi 2 or psi n happening will give us satisfy X equal to K. And I'm going to use this notation. Probability of X equal to K is N choose K, P to the power K, Q to the power N minus K. So your job is go home and try to plot this for different values. So let's say P is 1 over 10. And let's say N is 10 or 20. Let's say 12. So if you go home and plot, you will get this pattern. So there are a couple of homeworks related to this. So generally any binomial will sort of look like this. So what I'm plotting here is PK. PK is on the y-axis here, capital PK. Remember, don't get confused with this. There's only so many notations I can use. This P is the probability of getting a head in any one toss. Let's say 0.5 if it is a fair coin. This is probability of getting K heads in N tosses. So what is the probability of getting 4 heads in 10 tosses? You have to use this formula. N is 10, K is 4, P is 0.1, and you find out and then you plot it, you will see that you will get this shape. So what I'm plotting is against K. So this is K equal to 0, 1, 2, 3, up to N. So look at what I'm asking now. So I want to find out where is this K max. What is the property of the K max? Anyone look at the picture. Where have I marked K max? K is on the x-axis. Anybody? What does it mean, K max? Can anyone give me?
Highest probability at Kmax.
I know. What is Kmax representing in terms of probability? Look at the probability graph.
When x equals k max, the probability of that is higher than any other.
All right, so listen to what he is saying. So what we are looking at is the way I have written, Kmax has got the highest probability. That means if you perform this experiment, which value of head is most likely to occur? Anybody? If I toss a coin n times, what is the most likely value of k? Most likely means maximum probability. Anybody?
Half n.
What?
n by 2.
No, forget about n by 2. Look at the graph.
Kmax.
Kmax.
Most
Yeah.
likely. So there is a question related to that. You should look at my lecture notes. I have derived Kmax in terms of n and p. Remember, in this problem, there are only two quantities that you know. N is the total number of experiments. P is the probability of getting ahead. So we should be able to get Kmax in terms of. So you should be able to show that this Kmax is close to n multiplied by p. So how do you do it? So let me give you some clues for your homework. So the question is, what is Kmax? So its physical meaning is I hope you can read what I wrote. Most likely value of k in n tosses. That means that's the same as saying maximum probability. We want the value of k for which probability of x equal to k has maximum value. So look back at the graph. So this must be the most likely value because that has got the maximum probability. Unless two values are equal, then there are two values. So look at the graph. How do you, the question is, how do you find this? How do you, from the graph, what is the value of what is the property? Look at the Kmax. And if you change Kmax to Kmax minus 1 or Kmax plus 1, what happens to the probability? Anybody? Look at the graph.
It
Decreases.
Reduces.
Which one is the value? So I will write here. You have x equal to Kmax plus 1. And I have probability of x equal to Kmax minus 1. So what is the relation between these three probabilities? Anybody?
Left is smaller than mid, and mid is smaller than the right.
And how about here?
Also smaller. Or
Greater than or equal to.
This way or this way?
P, yeah.
Oh yeah. Yeah.
And remember, you go home and do this. You know how to write this. So this is n choose.
Professor, the graph is following a normal distribution and the Kmax.
Hold on. Let's not jump ahead. I'll come to normal, etc. later. All I'm saying is if you go home and plot it, it has got some shape. You will see that it is this shape, whether it is normal or something like a bell shape, it will come. But it will definitely, somewhere it will peak. Right now we are concentrating here. Let's just listen to me what I am saying. You'll have plenty of time to worry about normal. Okay? Yes?
Yeah, it's just the expectation, right? NP.
You're jumping too much. Just listen to
Okay.
I'm developing one theme after the other. Yeah,
Okay.
the graph you can see that if whatever, there will be one value at which the probability will be maximum. Yes?
Yes.
So we can call that the most likely value of k. That's what we are trying to find out. So I am explaining to you how to do the homework. This problem is there in the homework. So from the graph you can see that you should use this relation. This will be, instead of Kmax, I'm just going to call k. It's easy to write. So this will be p to the power k, q to the power n minus k. When you come here, replace k by k plus 1. So I'm going to leave it to you. and then you expand this and simplify, you will get the relation that n is close to, k max is very close to np. This is what you should be able to show. So what it says is the most likely value is n multiplied by p. So if p is half, what is the most likely value of p? Somebody told me n by 2, right? That's your common sense, right? And how it comes up is, this is the derivation. So I want you to go home and substitute both the places. Here it will be n p to the power k minus 1. So you have a little bit work to do. You simplify all the terms, you'll get an expression close to this. Any questions?
Hey, Professor. So we determined that that was the shape of the distribution just based off of this experimentation, correct? But how could we?
Let's not use unnecessary words. It's not a, I didn't tell you it is a distribution. I'm saying if you plot the probabilities against k, you will get that, you will notice that shape. So it's an experimental observation. Exactly, right.
Right, okay.
And
How could we know that that always holds true?
So why don't you, as I said, we will prove it later, but right now all you can do is you can plot a few cases and see that whenever you plot it, you will see it comes up to that shape.
Right, okay.
Little later, after a couple more classes, I will prove that it actually has a bell-shaped shape. Right?
Okay, okay.
But it is too early to jump into that right now. So let's understand it physically. Right? So you see, what I'm defining by a random variable is when you perform an experiment, we are interested in some outcome, but we know the possible values of that outcome, but which value it will take, you cannot determine beforehand. All you can say is figure out the probabilities of each particular value. That's the idea. So look at this here again. X is a random variable, n tosses, X represents number of tosses, number of heads in, so n independent tosses, let's say, of a coin with the probability of head equal to small p. This is where we start. X is the number of heads in n tosses. So X is a random variable because we definitely will not know what the value of X is. But we know that, so we want to find out the probability of X equal to k. This probability we just computed. It is n choose k, p to the power k, q to the power n minus k. K goes from 0, 1, 2, 3, etc. So if I draw this graph, this is the probability. So it looks like I'm putting masses all over, right? So this is called a probability mass function. So typically it will look like this in this case. This is, I called it to be a binomial random variable because you have a binomial expression here. So here I am plotting probability of X equal to k. We may use a description pk here. So when you toss a coin, what will happen? If you take the union of all this, what will you get? Anybody? When you toss a coin, a certain number of heads should happen. What could be those heads? It could be 0, or it could be 1, or it could be n. So what can you say about this union? Anybody?
It's one. Or this the whole set.
Whole set, not one, whole set. So if you take probabilities on both the sides, what do you get? What is the probability on the right side? Let me ask you that. When this happens, look at here. When this happens, can this happen?
No, they're all mutually exclusive.
They're all mutually exclusive. So the probability of their union is
the sum of each one's probability.
It will be 1 because it is the whole
exactly right. So look at here. You get this to be 1. Is this true? Let's plug in that formula. So we have summation k equal to 0 through n, probability of X equal to k. So that's a summation n choose k, p to the power k, q to the power n minus k, k equal. Anybody knows how, what this expansion represents? Anybody? This is a simple math problem. N choose k, p, a to the power k, b to the power n minus k, k equal to 0.
It is p plus q, q's
to the n.
To the
P plus q is how much?
1. Yeah, so it.
Okay, so everything checks. You see, this is the expansion of a binomial term. That's why we will call this random variable to be a binomial random variable. So I introduced one random variable. We will write it like this. So a binomial random variable x has got two parameters: the number of tosses. I'm sorry, a number of tosses and the probability of what is the probability. This need to be known. If it is 0.5 or 0.49, this need to be known, and we need to know how many tosses we are doing. Okay. So it has got two parameters, n and p. So I believe there are a couple of homework problems. So let me give you, to help you to solve this. So I believe this is part of your homework problem. So let's understand the notion of the meaning of at least and at most. So we know about probability of x equal to k. Of course, we studied probability of x equal to k is n choose k, p to the power k, q to the power n minus k. Can anybody relate to these two? K goes from, of course, 0, 1, 2, 3, etc. n. We know this event. We know the probability. Y is defined as at most n by 2 heads. How do you express y in terms of x? Anybody? Let me call this to be xk. Xk means x equal to k. X equal to k means k heads and n tosses. At most n by 2 heads means what? Anybody?
From 0 to n,
x0 plus x1 plus x to n by 2.
Not
x0.
plus, union.
Plus
Union, right?
Yeah, union. X n by 2.
This is also the same as saying that probability that, isn't this true? Number of hits are less than or equal to n by 2, right?
Yeah.
Again, these are all mutually exclusive. So what will be the probability of y? Anybody?
The sum of
Summation k equal
x
to 0 to
0.
n by 2.
All right. How about z? How will you express z in terms of x case?
k should be n over 4 and n over 4 to n.
In terms of xk, at least n by 4 heads. That means what?
K is n over 4.
Z is n over 4?
Is x n over 4 union
No, I
x
mean,
n over 4 plus 1.
so this is the same as saying the x is less than or equal to n by 2,
Y
right?
minus
Right. But don't you see that you can also write it like this, right?
Yeah.
What you said is right also, yes. So all these are true. So let me, probability of z is x is greater than or equal to n over 4, right? That's the same as 1 minus probability of, here you have to be careful. If you put a greater than here, this should be only n by 4. So this will be summation of x equal to I or k. K goes from 0 through where? Anybody? 1 minus k equal to 0
4
through
minus 1.
N by 4.
N by 4 minus 1.
n by 4 minus 1. This you should be careful here, right? So this comes up in the homework, at least, at most, etc. So I hope you understand now, at least, at most. So remember, at least means x is greater than or equal to something, right? At most means x is less than or equal to something. So look at this problem. A box has 10 components. Each component can be defective with the probability small p. So a box has got 10 components, each 10 bulbs. Each bulb can be defective with probability p. So if so, what is the probability that whatever, let's say at most 2 components are found to be defective? So you check all the 10 components. At most, so we are going to define y to be at most 2 components are defective. How will you formulate this? Anybody? At most means what? I just went through this.
Maximum.
Let x represent the number of, so you say x is number of defective components in 10, totally in the box, number of defective components in the box. So probability of y is the same as x is less than or equal to 2, right? At most 2 defective components. Yes? Yes or no?
Yes, sir.
So here I can write it by hand because there are only 3 cases, x equal to 0, 1, 2. And then you just use the formula. So this will be k equal to 0 through 2, n choose k, p to the power k, q to the power n minus k. So this is a quality control problem. You substitute the value of, let's say p is 1 over 20. Okay. So you plug it in here. So q is 19 over 20, n is 10, k, you just compute this. And if this probability is let's say 0.3, you make a decision saying that so we want to compute this probability. If this probability may come out to be 0.2 or 0.3, whatever, and then you can make a decision whether to accept this lot or the lot or reject the lot, etc. So I think you will be able to do the homework problem now based on, so at least at most, etc. comes up like this. Any questions? So I'm going to move on again, connected with the binomial. So we are talking about binomial random variable. So essentially k heads in n tosses. That's what the random variable is representing. So it has got 2 parameters, n and p. X is k heads in n tosses. Probability of x equal to k is n choose k, p to the power k, q to the power n minus k. Let me introduce a related random variable. You take a course many times till you succeed. So sometimes we are in, to get to something, you need to do multiple trials, because the first time you do it, you may fail. Second time you try, you get a tail again. So you keep trying till you get a head. So what is the unknown here? Anybody? I give you a coin. What is the unknown here? The coin is
Probability of success or head.
what?
The number of experiments
Oh,
in total.
yeah, okay.
What is it?
The number of experiments in total
Yeah,
until the first success.
how many times you have to try till you get to a head? Exactly, right. So that's even if I give you a coin, and even if I tell you it's an unbiased coin, still it is not clear how many trials it could take. So you can see there is another idea of a random variable. So y is another random variable. So that means what? Let's say y is k. What does that mean? Y equal to k means what? What will be the experiment will look like what? Anybody? Hello, you need to think.
K
What?
minus 1 tails and 1 head.
What?
K
It
minus
means
1
that
tails
for
and
the
1 head.
Yes.
yes.
That means when you tried first time you got a tail, and then a head. So kth time you got kth trial you got head. Remember, all these are independent trials. So what is the probability of y equal to k? Anybody? All these are independent trials. So it's the product of the probability. So it is probability of t multiplied by probability of t, etc. And this is all QQ, QP. Yes? So it could be on the 1, 2, 3, etc. I mean, k minus 1. It should be, k could be 1, 2, 3, etc. up to infinity. So I'll write it in the, so if you define y to be the number of trials to the first success, probability of y equal to k is, it looks like pq to the power k minus 1. K can go from 1, 2, 3, etc. up to infinity. Look, if you plot this, will the first one will be p, then it will be pq, then it will be pq squared, etc. pq to the power k, etc. K is what we are plotting. So this looks like it is a geometric progression. So we call this random variable a geometric random variable. That's the name attached to it. So the geometric, physically you should know that this represents the number of trials required to the first success. So there is a homework problem connected with this. So anybody, what is the probability of getting a hit in 2 trials? Anybody? From this problem. Probability of hit appears at the second trial. So what will be the probability?
PQ.
PQ. What is the probability that the hit appears on the 4th trial?
PQ.
6th trial? 6th trial will be PQ to the power minus 5, right? So your homework problem is this one. Can you read what I wrote? What is the probability that a head appears on an even toss or on even trial for the first time? So call y equal to 2. Y equal to 2 means head appears on the second trial. Y equal to 4 means head appears on the 4th trial. How do you, let me call this to be z. How do you relate z to y? Anybody?
Z equals y equals 2 union y equals 4 union y.
So let me call this to be yk. So this will be y2. What did you say?
Y2 union y4 union
All the way
y
to
all even number.
all right, very good. So you need, and all these are mutually exclusive. So you go home and compute it. That's how you do that problem. Okay. And similarly, you can do the other way. What is the probability that a head will appear on an odd trial? So if you go to the a casino, then you can, figuring out that probability, you can do the betting and so on. The question is, if you have a coin whose head is P, which probability is higher? Head appears on the even trial or odd trial? So I'm going to leave it to you to find out. So let me define Y to be the first head appears on the nth trial. So probability of Y equal to n is what? Anybody? We just went through it. First head appears on the nth trial. So probability of Y equal to, that it takes n trials is equal to what? What is the probability?
P into Q power
Q
K minus 1.
minus 1.
N minus 1. N can go from 1 to all the way to infinity. Okay. I'm going to generalize this. So all these are discrete random variables, because if you plot this, I don't know whether I mentioned this. When I plot this, these are looks like masses. So this graph is called probability mass function. And let me also ask you this: if you add up all this probability of what will you get? What will be this even? Y equal to 1, or Y equal to 2, or Y equal to 3, etc. So one of these has to happen. So this whole thing will be the whole event. So I hope you see this, right? Probability of Y equal to K, K from 1 through infinity is equal to 1. In other words, all these probabilities add up to 1. So this is called a probability mass function, and it again has the same property. All of them is 1. So I'm going to generalize that this is known as the geometric random variable. And now I'm going to generalize it to a something called you need to pay attention to what I'm trying to say here. I'm defining a new random variable. I hope you can see here it was the first head. First head appears on the nth trial. That means you just want to succeed. Here you want success after success. You want K head. But the Kth head is going to show up. So when the Kth head comes, the last one is going to be the Kth head. And this is the nth trial. Then you stop. So when you see the Kth head, you stop. What happens before that? Anybody? So if this is the Kth head in n trials, what must be happening before that? Anybody?
K minus 1 heads in n minus 1 trials.
Let me call that to be an event W. So you have W union this H, right? And these are mutually exclusive. I'm sorry, the intersection, right? These are mutually exclusive. No, I mean, they are independent because one after the other. They are independent. Because this and this, not union, or not or, independent. Right? So look at here, Z is, so once again, Z is kth head in nth toss. So probability of Z equal to n. So n is what we are interested in. Number of heads are fixed, K heads. So this is the same as probability of W multiplied by probability of head. What is W here? Look at W. W says K minus 1 heads. It doesn't matter. You just need K minus 1 heads in n minus 1 trials. We have studied this random variable. Anybody can tell me what is the nature of the random variable W? We just studied it. What is that?
Binomial.
Exactly. That's a binomial random variable, because here we don't need heads in any order. We just need K minus 1 heads, K minus 1 successes. So this is a binomial random variable with the parameters n minus 1 and p. So we can use the binomial formula somewhere here. This is the binomial formula. So n minus 1 and p. How many heads? Anybody? It is k minus 1 heads and n minus 1 trials. This was k heads in n trials. So I'm just going to replace k by k minus 1, n by n minus 1. So probability of this is going to be n minus 1, k minus 1, choose p to the power k minus 1, q to the power n minus 1 minus k minus 1, multiplied by probability of head, which is p. So if you put it together, n minus 1, k minus 1, p and this, so you get p to the power k. If you expand this, n minus 1 minus k plus 1, so this is q to the power n minus k. What is the variable here? N. N goes from k, k plus 1, etc. To get to k heads, you at least need n trials. And this z is known as, for whatever reason, this is known as a negative binomial random variable. So I hope you see where I am jumping, I am going, developing one after the other. We had geometric random variable, which was the first head in n tosses, and then we said we want the kth head in at the end of the toss. So n is the variable. We don't know how many tosses it takes, but at least it will take k heads, k tosses, right? If to get a k heads, the best thing that will happen is head all the way to k. So look, it is very close to binomial, but it is not exactly binomial. It's a different, again, you can plot it. So if you plot it, it will go up something like this. So a probability mass function, let's say Pn. So summation Pn n equal to k through infinity is 1, right? So k is fixed, k heads. Try to understand this because I'm going to do a problem on this, an interesting problem on the binomial random variable. Any questions on this negative binomial? So remember, binomial, think about it. The binomial random variable deals with, there the number of tosses are fixed, n tosses. Question is how many heads you get. Here the number of heads are fixed, k heads. Question is how many tosses you need. So it's just the complement. That's why it's called the negative. In the first case, binomial, number of tosses are fixed to be n. Question is how many heads can you get? What is the probability of getting k heads? In the negative binomial, you fix the number of heads to be k. Then you ask the question how many trials you need. So obviously the last one is going to be a head, because as soon as you get the kth head, you are going to stop. So that's the way you have a head, and then before that you have a head, and before that you have k minus 1 heads and n minus. So this is the formula, right? This is formula for negative binomial random variables. N goes from etc. So you plot it, you will get something like this. So look at this example. So in baseball, you have two teams. They play against each other. Let's say that probability, of course, each depending on who is your opponent, your probability will change. If the Mets are playing against the Yankees, that's one show. If the Mets are playing against somebody else, their strengths and weaknesses will depend on the opposite team also. So let's assume this is P, and of course the probability of B will be Q. So usually when you come to the finals and so on, these two teams are almost very equal competence. So one team may be 0.51, the other team is going to be 0.495, etc. You are never going to get a case where one team is 60%, 0.6 and this is 0.4. That's the whole point of playing a lot of games and eliminating all the weaker terms. So when you come to the final match, you have more or less two equally competent terms. And anybody knows in the baseball final series, how many games do you play to win the series? Anybody? Hello?
At most 7. I don't know.
Yeah,
I don't know, honestly.
So you have to play the teams can play up to 7 games, and who wins what is the rule? Who wins the series? How many games do you have to win the series?
4 games.
4 games.
Right. The team which wins, team that wins 4 games out of 7 wins the series. Okay. So the question is, what is the probability that, this is our question, what is the probability that team A wins the series? So I'm going to do this, remember, so this is a useful problem. How do you compute it? And I'm going to show you that the negative binomial is going to be helpful here. So think about it. For any team, A or B, to win the series, you have to win 4 games. So how many games do they have to play? Anybody? To win 4 games, how many games do you have to play?
At least 4 games.
So at least 4 means what? 4 or
5 or 6 or 7.
Right. So let me define xk to be you need 4 wins in k games. As you said, k has to be 4, 5, 6, 7. So let's compute the probability of this means the 4th win is going to be at the kth game, right? Yes, because when you get the 4th win, the game is over. So you can see we want, this is exactly this problem, the previous problem. Kth head in nth toss. So we want the fourth win in the nth toss. Here n can go from 4, 5, 6, 7, etc. So let me change this to n. N can go from 4, 5, 6, 7. K is 4 here. 4 wins. Look at here. Kth head, kth win in n tosses, n games. K is 4. 4th win. So this is going to be probability of xn is going to be, anybody? N minus 1? Look at here. What is it? K is 3. K is 4.
And P4 Q
N minus 4, right? N can be 4 or 5 or 6 or 7. So that's good. Now, okay, let me complete this problem. So A will win if A can win in 4 games or 5 games or by playing 6 games or by playing 7 games. All these are mutually exclusive. So the probability that A wins is the sum of the probabilities, right? So this is, I want you to go home and compute this and plot it and see how it comes up. So this is going to be n minus 1, choose 3, p to the power,
P4
right?
minus P and minus 4.
So look, n equal to 4. Let's say P is, why don't you go home and do this? I want you to, let me call this probability to be PA. I want you to plot PA as a function of P. This is P here. Remember, there's only one variable is P. So P goes up to 1.4. I'll tell you how it goes up qualitatively. So if you play 7 games, it's going to go like this. That means this is for, let's say, 7 games, okay? So if you play 7 games, it will come like this. That means if it is you can see a team with a point, if your probability is P equal to 0.1, this may come out to be, let's say, 0.55. So 0.51 here will become 0.55. So if you have a slight advantage, it gets a little better. But the interesting thing is, nobody has the time. But suppose you are allowed to play 99 games. So I want you to plot it. Then you will see that this is what will happen. Suppose you are allowed to. So remember, here only 7 games. Here I am playing 99 games. Let's say. Then you will see that this curve will go like this. The implication being, the team which is little better will surely win. I hope you see this. So you can use this in communication problems, etc. So this is the one with where 99 games are played, or some odd number, 51 games. So remember, in baseball you can do it, except it will take 3 months. So that's the reason, and nobody will come for it. It will get boring. It's the same team being. But if you allow to play, so the whole. But in a communication theory where you are doing it 1-0 or filtering, you can use this idea. You can do it repeatedly just to make sure who is whether it is 1 or 0. So you can think it of, this is also the idea of coding, right? Whether because of the noise, the bit is, so you can make it through something like a base symbol filter, and then see how many maybe you chop the data into n sequences and see how many hits are there. So if you get more than then you decide in favor of 1 or 0, P representing 1, etc. The probability of getting the bit 1. So again, you will have to think. You can see there are ideas here which you can use it for communication, for say, bit detection, communication theory, and so on. I hope you understand this problem. So what I want you to go do is, for extra credit, I will do it. If you submit it to us, we will look at it. Plot PA for 7 games, which will be in green, and let's say in 51 games or 99 games, and you will see that the curve is going to hug like a step function. So the moral of the story is, a team with slight advantage, if you repeatedly perform the same thing, you will end up being a winner. And this is the principle being used by the casinos. The casinos have the slight advantage, and they are playing the same game against you or your friend. So each person, they are playing the same game, but they have slight advantage. You can see, if you increase the number of games, the probability that the person with the slight advantage will win. So that's the principle of all the casinos. Any questions? So remember, I introduced you binomial random variable, geometric random variable, negative binomial random variable, and there is a simple random variable in that context called the Bernoulli random variable. So Bernoulli random variable only takes two values, x equal to 0 or x equal to 1. So this is the same as tossing a coin once. X represents the number of heads. You are only tossing it once. So probability of x equal to 0 is q, probability of x equal to 1 is p. So if you plot it, at 0 you get a q, at 1 you get a p. So this is a Bernoulli random variable. So Bernoulli is a special case of binomial, right? Because in binomial you could toss n coins. So you put n equal to 1, you get this case. Binomial is n comma p. So I hope you see this. Bernoulli is same as binomial. What is the value of n? 1 comma p. When you put n equal to 1, just toss a coin once, you get. So that's a very special case. And the p plus q is 1. So this is the probability mass function. So we did binomial, Bernoulli, geometric, and negative random variable. Let me now do another interesting. So all of these are physical. And next week I will make it a little more formal and consider the case where the random values take continuous values. Right now, all random variables take discrete values. So you can call these random variables discrete random variables. So what we have figured out is discrete random variable takes specific values with a certain probability, and plotting that probability against the discrete value gives us the probability mass function. And if you add all of them, because something has to happen, so the probability of the whole mass function is 1. Also, let me talk about rare events. So you can say in a highways, especially like in New York, the FDR, it's a very busy highway. And I don't know, if you travel in that, you can see that there is an accident more or less every day, maybe multiple accidents. So it's a what is the probability of an accident somewhere in the FDR? I don't know. You can say maybe 1 over 1,000 or something. In 1,000 cars, maybe 1, or in 10,000 cars, 1 accident, something like that. So of course you can, they have the data because people know how many accidents happen, so you can figure out some number. So again, it's very rare. It's not like every car is getting into an accident, right? So it's a rare event. Accidents are rare events. But on the other hand, especially in the US, I suppose India and China also, there are a lot of cars, right? So the number of, so if you are an insurance company, you are interested in the total number of accidents. And you know that accidents are rare and the number of cars are very large. So you'll say, okay, I'm going to use the, so X represents the number of accidents. So probability of each accident is very small, but n is very large. So if you ask what is the probability of k, you can say, of course, this is n. I can model it as binomial because an accident is like a head. So probability of getting k heads in n tosses. So you can make this model. But the problem is it's very difficult to compute this. Suppose n is million and p is 1 over 10 to the power 5 or something. So for rare events, how do you compute this? So that's what I'm going to talk about. So when you say if p is extremely small, that will be a rare event. So I'm going to talk about rare events in the context when the number of events involved, number of entities involved are very large. So think of binomial. So what happens to this binomial? The question is, what happens to this probability in the limit as p goes to 0 and n becomes large? So that's what we are going to. So once again, x equal to k, but I want to consider in this context of p going to 0 and n going to infinity. So in other words, the probability of a head happening is extremely small. Probability of an accident happening is extremely small, but there are a large number of causes. There are a large number of automobiles. So each one can have two states, accident or no accident. Because it is extremely small, most of the days you go through without any accident. But the question is, if you have a large number of cars in the highway, what is the probability of having k accidents? That's what, in this limiting case, that's what we are going to analyze. So the probability of this is n choose k, p to the power k, q to the power n minus k. We want to, so again, we want to analyze this limit, p tends to 0, n goes to infinity. So I'm going to expand this. So this is n factorial divided by k factorial, n minus k factorial, p to the power k, q to the power n minus k. I'm going to cancel n and n minus k factorial. So I can write this as I can write it like this. K factorial is here. When I cancel with this, I get this term. Now watch what I'm going to do. I'm going to divide this by n to the power k, and I'm going to multiply by n to the power k. And I'm going to take one n here, one n here, one n here, etc. Okay, I multiplied by n to the, so this is going to be n over n, and this is n minus 1 over n. This is n minus 2 over n, etc. And here I have np to the power k, and here I have 1 minus p to the power n minus k, and there is a k factorial here. N over n is 1. This is 1 minus 1 over n. This is 1 minus 2 over n, etc. 1 minus k minus 1 over n. Then let me call np. So I'm going to assume that p goes to 0, n goes to infinity, such that their product np is a constant. So in some cases it may be true, in some cases this may not be true. So wherever this is true, this approximate, whatever our argument will look. So np is lambda to the power k over k factorial. Here I have 1 minus, I'm going to write it as np over n minus k. So I multiplied and divided by n here, but np is lambda. So I'm going to redo all this in the next page. So probability of x equal to k, and we want this in the limit p goes to 0, n goes to infinity, such that np is lambda. So this is the key. So this is from here 1 over n, etc. 1 minus k minus 1 over n, then lambda to the power k, k factorial, all this is here. And here this is 1 minus lambda over n. Remember, np is lambda. And here I have n divided by 1 minus lambda over n to the power k. N minus k, I wrote it like this. So now let's look at it carefully. Now I'm going to push n to infinity. Look at on the right side, there is no p. I'm going to push n to infinity. When I push to n to infinity, all this will become 1. The key is here, there are only k terms here, k terms, not infinite terms here, k terms. So 1 multiplied by 1, etc. will be 1. So this will go to 1. So this will go to, so probability of x equal to k tends to, limit p tends to 0, n tends to infinity. This will be 1, 1, 1, lambda k over k factorial. And look at the denominator here. K is a finite number. When n is pushed to infinity, this is only a finite number. This will, lambda over n goes to 0, 1 to the power k goes to 1. But what about here? So the key is here. I think somebody told me the answer earlier. 1 minus lambda over n to the power n. What happens to this term? Anybody? Someone?
E to negative lambda.
E to the power what?
Negative lambda.
Right. So this becomes e raised to minus lambda. So we get this interesting thing that if the p is very small, if you perform, if you toss a coin a very large number of times, the probability of getting k heads, I don't need to know what n is. N is extremely large. Look at the way things are going. The number of cars in the highway are extremely large, and each accident is extremely small. So what is the probability of getting k accidents? Exactly this. So this is e raised to minus lambda, lambda k over k factorial. K could be 0. Remember, it's a binomial. K is 0 through n, but n goes to infinity. This is the probability of x equal to k. So we can call this to be, this will be a new random variable. So this is called a Poisson random variable. Is this limiting case. So Poisson is a limiting case of binomial. So in a binomial, let's say, I'll give you an example. A space shuttle or an aircraft, I'm just going to make up numbers, has got 1 million parts. So you can see n is large. And each part is made very carefully because after all it's an airplane. You don't want it to fail while it is flying, right? So the probability that any one part will go bad is extremely small. Let's say 10 to the power minus 5. So P is very small. Let's say if one component fails, maybe the pilot can bring the aircraft to, somehow he can bring it to safely. So the quality control is that when the plane is flying, I'm just going to make up something. You don't want more than 3 components to go bad. So if more than 3 components go bad, then the plane will collapse. So we want to compute the probability that what is the probability that there will be an accident. So the probability that there will be a fatal accident will be the number of failures is more than 3. And you can see, you can approximate it by Poisson because probability is very small, n is very large. So all that matters is lambda. Lambda is the NP. N is 1 million, P is whatever. I told you, let's say 10 to the power minus 5. So NP is 10 to the power minus 6. So n multiplied by P is 1. Lambda is 1. So lambda is 1, and we want to know what is the probability that the number of failures are less than or equal to 3. So that's going to be failures is 0 or 1 or 2 or 3. So probability of k failure is e raised to minus lambda, lambda k over k factorial. Then you sum it up. So if x is Poisson with parameter lambda, probability of x equal to k, you can think of this as the failures. K failures is e raised to minus lambda k over k factorial. K could be 0, 1, 2, 3, all the way up to n. That is all the way up to infinity. So probability that the failures is less than some number k0 means probability of x equal to 0 or x equal to 1, x equal to 2, etc. up to k0. So this is sigma k equal to 0 through k0, probability of x equal to k. Probability of x equal to k is here. So it's very easy. You just plug it in, e raised to minus lambda lambda to the power k over k factorial, k equal to 0 through 3 in your case, or k naught. This is the probability of the system failing. So a space shuttle, same thing, right? Space shuttle has got whatever, 10 million components. Each component is going to fail only with a very tiny probability, 10 to the power minus 6 or minus 7. So what is the probability that the shuttle will collapse? So you say the shuttle will collapse if 5 or whatever, I'm just making up. They know more than 3 components go bad, then it may collapse. So the probability of the shuttle collapsing is the number of components failing is going to be less than or equal to 3. So you compute this, and if this number comes out to be 0.7, then don't fly the shuttle. It means it's highly likely it will fail. But if this number is extremely small, then it is fine. So that's how quality control is done. Any questions? So this Poisson is you may say, oh, Poisson, who cares? Entire queuing theory is built on Poisson, and this random variable will keep coming to us. So you better try to understand the concept of Poisson. So Poisson represents rare events. We will also have a Poisson process later when we study stochastic processes. So whatever, if these are, another way to capture is, if this is time, these are the accidents happening, or whatever, or telephone calls arriving. They don't arrive, so sometimes it arrives, then you have a waiting time, then it arrives. So, you can take some time instant t and ask what is the number of failures, or in 0 to t. So if start from 0, what is the number of failures? This is the first failure, second failure, third, ith, etc. This is what is the probability that the number of failures is k. So that's e raised to minus lambda k over k factorial. So this comes up in many ways. The lambda, of course, has something to do with the duration that you are looking for, etc. Any questions? Anyone? Hello? Camila? Naiva?
Hello?
Any questions, or you understand?
No, yeah, I think I'm understanding, yes.
Very good. So we went through Bernoulli, binomial, geometric, negative binomial, which is the baseball experiment, when the k hits in n trials, k hits in n trial. The kth hit in n by nth trial. That's what the negative binomial. Then I came to this rare events, Poisson. So remember, Poisson, if you look at it, there's only one parameter. So you saw the connection between binomial and a binomial where p goes to small and n becomes large, such that np is lambda, becomes Poisson. So you can see the connection with the parameter lambda. Lambda is np. So so this is a rare event, right? So people, military goes to fight, and especially in the peacetime, nobody is going to die in the army. But still, once in a while, something happens, and so you could ask the same question on a peacetime. The soldiers dying is a very rare event, right? So what is the probability that? But once in a while you hear, like in Afghanistan, a couple of soldiers died and so on. So what is the probability that this year there will be 2 deaths or 3 deaths? So that's those are all Poisson random variables, rare events. So rare events, you model it as Poisson, and it has got one parameter lambda. Again, if you plot it, it will look like this: x equal to 0, x equal to 1, x equal to 2. At some point, it will start decreasing, and it will go down. So the probability mass function will look like this. So what I'm plotting here is probability of x equal to k. K goes from 0, 1, 2, all the way to infinity. So if you add up all these probabilities, k equal to 0 through infinity, you will get 1 also. So this mass function adds up to 1. So today, purposely, I am only talking about discrete random variables, just to give you a flavor of, to connect it with the physical reality. And in the next week, I'll get a little more abstract and start dealing with random variables which are continuous values like noise and so on. Right? We have to, that's the whole goal here. So I took a different approach this time. Maybe introduce things which are like a coin tossing, right? Introduce the binomial random variable, Bernoulli random variable. So we went through 4 or 5 random variables. So before I stop, let me also do a generalization of binomial. I mean, now this you should be able to read and see a few more cases and so on. I think the lecture 2 would be my notes. You should go through this at this point. So what is binomial versus? So binomial, as it says, you only have 2 basic events, head or tail. Probability of head is p. Probability of tail is 1 minus p, which is q. Whereas here you have multiple options, a1, a2, etc. Let's say am. The probability of a1 is p1. Probability of a2 is p2, etc. Probability of am is pm. So what is a good example? So this will be, for example, tossing a dice. It has got 6 options. So here you ask, here you can only ask x is k heads in n tosses. So we know this probability. It is n factorial divided by n minus k factorial, n minus k factorial. And multiplied by p to the power k, 1 minus p to the power n minus k. Where here, so the x will be, if you toss, let's say k1, k1 times a1, the event a1 occurs k1 times, k2 times a2, etc. km times am. So we want the probability of this. Of course, k1 plus k2 plus km will be the total number of tosses. So look at here. K heads is the same as saying k heads in n tosses, means k heads and h appears k times and tail appears
n minus k.
n minus k times. So that's a generalization of this. Head appears k1 times. The second, a2 appears k2 times. am appears km times. So here you can write this if you want. K times head and n minus k times tail. So that's the corresponding event. And so the probability, so the probability of this, I'm just going to give you the formula. This is n factorial divided by k1 factorial, k2 factorial, etc., km factorial. So exactly the same as here, p1 to the power k1, P2 to the power K2, Pm to the power Km. Remember the K1 plus K2 etc. Km is n. Similarly, of course, P1 plus P2 plus etc. Pm equal to 1. Because like here, P plus Q is 1. So that's why I did this in parallel. So this is binomial, this is multinomial. So let me give you let's do an example. A dice is tossed 10 times. Remember, a dice has got 6 faces. Find the probability of So how do you solve this problem? Is this a binomial problem or multinomial problem? Anybody?
It's a multinomial problem.
Is it multinomial? Look at what we are interested in. Let's go for interested in. You are interested in A1 if you compute here. When you perform an experiment, you have multiple outcomes, A1, A2, AM. Here what we are interested is, let's say, go by our interest. A1 is F1, A2 is F2 and F4. And then what? Is
A3,
huh?
A3 is F3, F5, F6.
Right, because remember, nothing. When you perform the experiment, you are going to get the other ones also. So if you toss it 10 times, you can get this or this or this. Depends on the problem. Of course, we know what is the probability of A1. Anybody?
1/6.
1/6. P2 will be probability of
1/3.
These two are disjoint events or mutually exclusive. It's 1/6 plus 1/6, 1/3, right? And probability of A3?
1/2.
Huh? Half, right?
Half, yeah.
All right, so now look at the question. The question is, what is the probability of, so what we are interested is F1 occurring 2 times A1, and 3 times A2, but you are tossing 10 times. What does that mean? Anybody?
5 times A3.
Yeah, that's the thing you have to fill up. So 5 times. So what we are interested in is A1 occurring 2 times, A2 occurring 3 times, and A3, then A3 must occur 5 times. So the probability of x equal to this is 10 factorial divided by 2 factorial, 3 factorial, 5 factorial, P1 to the power 2, what was it, P2 to the power 3, and P3 to the power 5. Okay, so this is the way you solve problems of this type. So multinomial is, of course, the same problem. Let's look at the same problem. A dice is tossed 10 times. So let's say this is part A. Part B is the same. A dice is tossed 10 times. Suppose what is the probability of F1 occurring 2 times, F2 occurring 1 time, F3 occurring, let's say, 2 times, F4 occurring 1 time, and F5 occurring, let's say, 3 times, and F6, so this is 2 plus 1 plus 3 is 5, 6, 9. So that means F6 has to occur 1 time. So this is a multinomial problem with how many, M is what? Same problem. Here you have A1, A2, A3, A4, A5, A6. Yes?
Yeah.
And then you know the probability. P1 is 1/6, P2 is 1/6, P3 is 1/6, P4 is 1/6, this is 1/6, this is 1/6. Then you put all these numbers and you will get, you plug it into this formula with M equal to 6, etc. So it depends on the description of the problem, right? And so that was whereas, so that's, so if